Let us discuss this Cauchy's quartz inequality. It's very important inequality we use at several places in mathematics. Okay, so let us prove it first. After that, we will discuss few examples on that. What we have here, we have a real numbers a1, a2 and ak, as well as b1, b2, bk. All these are real numbers, and for those real numbers we have to prove this inequality. So let us start to prove. We know that square of any real number cannot be negative. So that basic information I am going to use it here to prove this inequality. Let us write it. Clearly, x square is greater than or equal to 0 for all x belongs to R. For any real number, square cannot be negative. So what I am going to do, I am going to take x is equal to ai bj minus aj bi. Let me write that thing here. So therefore, ai bj minus aj bi square, that is also greater than or equal to 0 for all I running from 1 to n and j also running from 1 to n. It doesn't matter what is inside the bracket, square is there. That means 100% it is non-negative. It is true for all I and j running from 1 to n. So that's why we can take two summations here. If you add non-negative numbers, so again we will have non-negative numbers. So therefore summation I running from 1 to n, j running from 1 to n, ai bj minus aj bi square, that is greater than or equal to 0. After that, I am going to expand this bracket. You know that a minus b bracket square formula, a square minus 2ab plus b square. So let us apply that formula here. So therefore, summation I running from 1 to n, summation j running from 1 to n, I am expanding this bracket, ai square bj square minus 2 into product of these two, ai bj aj bi, okay, plus square of last term, aj square bi square greater than or equal to 0. So after that, I am going to take separate summation, as well as if there are any constants, I am going to take them outside. So therefore, there is no more space to write. Make a screenshot of it, then we will go further. Let us continue. I am taking separate summations. Summation I running from 1 to n, summation j running from 1 to n, yes, ai square bj square minus 2 is a constant, so we can take it outside. So 2 summation I running from 1 to n, j running from 1 to n, ai bj aj bi, right, plus summation I running from 1 to n, j running from 1 to n, aj square bi square. And the very important thing is that it's greater than or equal to 0. This is a very important thing. This step is not required. Let me remove this one. It is not, we have used it. You have make a screenshot of it. Okay, let us go further. See, here I and j are independent on each other, so those terms I'm going to take outside. So therefore we'll have like this, summation I running from 1 to n, ai square into summation j running from 1 to n, bj square, correct, minus, here also I will do the same, summation 2 into summation I running from 1 to n, ai bi, summation j running from 1 to n, aj bj, plus there also I will do the same thing, summation I running from 1 to n, j running from 1 to n, sorry, aj square into summation I running from 1 to n, bi square, that is greater than or equal to 0. This thing we have got. Okay, see, if you write in summation, if you write I, j, k, doesn't matter. So see, I am going to express the all summations with the help of k, variable k I am going to use. So therefore it will be like this, summation k running from 1 to n, ak square. Simply I change the notation. Instead of I took there k. Here also I will do the same. So therefore, summation k running from 1 to n, bk square minus 2, summation k running from 1 to n, ak bk. Here also summation k running from 1 to n, what I supposed to write? Ak bk plus here also I will do this same summation k running from 1 to n ak square, and here summation k running from 1 to n bk square, and the important thing is that is greater than or equal to 0. So that means summation I use k only. Okay, so what will happen because of this? See, this term and this term are same, getting? So these two brackets and these two brackets are same. So if you add, we will have 2 into these two brackets, right? Product of these two brackets. Make a screenshot of it, then we will go further. See, these two brackets are same. So that's why if you add, we will have 2 into summation k running from 1 to n ak square, right? Summation k running from 1 to n bk square, right? Minus product of these two brackets minus 2 into what we have here, summation k running from 1 to n ak bk, right? And this bracket is also same, no? So if you have product, suppose this is x, this is also x, x into x, you know, x square. So that's why I could write this is bracket square greater than or equal to 0. So this step is not required. We have also made screenshot of it. Let me remove this part, then we'll go further. Okay, it is removed now. So let us continue. Okay, so see, I will cancel 2 from both sides. So what will happen? So 2 will get cancelled, and therefore summation k running from 1 to n ak square summation k running from 1 to n bk square, right, minus summation k running from 1 to n ak bk whole square greater than or equal to 0. So obviously my next step is to shift this bracket on that side. It has a minus sign on this side, so if you shift it there, it will have a plus sign. So therefore summation k running from 1 to n ak square, right, summation k running from 1 to n bk square, I am shifting this bracket to that side, greater than or equal to summation k running from 1 to n ak bk whole square. Okay, so actually we have proved it here, that Cauchy's quartz inequality, but see, in a statement they have mentioned this right hand side in the left hand side, so simply I will interchange, so we'll have a required answer. So therefore I'm writing that thing here. See, actually both of them have a same meaning, getting? AK bk whole square less than or equal to, here we have a same thing in terms of greater than or equal to, I am writing in terms of less than or equal to summation k running from 1 to n ak square into summation k running from 1 to n bk square. So in this way we have proved this Cauchy's quartz inequality. After that, using this inequality, we are going to solve two examples. Make a screenshot of it, then we will discuss examples. Let us solve this example using Cauchy's quartz inequality. What we have in this example, we have three real numbers a, b, c. All of them are positive. And they satisfy this inequality, a plus b plus c less than or equal to 3. Then we have to prove that 1 by a plus 1 by b plus 1 by c greater than or equal to 3. Let us start with the given information. We have, I will mention clearly, what we have, a, b, c are positive real numbers. So that's why it is possible to take their square roots. Okay. So see, for Cauchy's quartz inequality, we need to have some finite sequence of real numbers. Getting? So let us take see what I'm taking three numbers, a1, a2, a3, okay, and these three numbers b1, b2, b3. So we can apply Cauchy's quartz inequality for these real numbers. Okay, so my a1 is root a, a2 is root b, and a3 is root c. And what will be our b1, b2, b3? I will take their reciprocals there. These are positive real numbers, so no need to worry. Okay, so those numbers cannot be 0. 1 upon root a, 1 upon root b, and 1 upon root c. So now I am going to apply Cauchy's quartz inequality for these 6 real numbers. Okay, so by Cauchy's quartz inequality. What can I write? You'll remember na Cauchy's quartz inequality. We can write A1 B1 plus A2 B2 plus A3 B3 square less than or equal to. So if you take square and okay, so this is left hand side, right hand side will be A1 square plus A2 square plus A3 square into B1 square plus B2 square plus B3 square. Because of Cauchy's quartz inequality, we could write it. Okay, so let us put their values. What is A1? We have those values here. So therefore root A, B1 1 upon root A, right? Plus A2 root B, B2 1 upon root B, A3 root C, B3 1 upon root C and whole square less than or equal to. So let us find the value of this first bracket, A1 square. See, it's square. If you take square, square root will get cancelled to each other. So therefore, we can write A plus B plus C since we are taking squares. Getting? And already they have a square root. So square and square root will get cancelled to each other. B1 square. This is 1 upon root A, but we are taking square. So that's why 1 upon A. Here B2 square means 1 upon B and B3 square means 1 upon C. So this thing we have. See, we have some space here. Let us use it. See, root A and 1 upon root A will get cancelled to each other. We will have 1 plus root B, 1 upon root B will get cancelled to each other. 1 root C, 1 upon root C will get cancelled. 1 square less than or equal to A plus B plus C, and is 1 by A plus 1 by B plus 1 by C. Okay, simply copy paste I have done there. See, A plus B plus C, they have mentioned something here that is less than or equal to 3. So that's why this is less than or equal to 3. 1 by A plus 1 by B plus 1 by C. So therefore, what will happen? In left hand side we have got 1 plus 1 plus 1, that means 3 square, that means 9 less than or equal to 3, 1 by A plus 1 by B plus 1 by C. What will happen? We can easily cancel 3 from both sides. So that's why 3 will get cancelled and we will have 3 less than or equal to 1 by A plus 1 by B plus 1 by C. So yes, we have proved it. So in this way we have finished first example. Let us discuss one more example. Make a screenshot of it first. Let us discuss this example. So in this example we have 3 real numbers A, B, C. And for these 3 real numbers we have to prove this inequality. So let us start with given information. We have A, B, C are real numbers. See, I am going to apply Cauchy's quartz inequality. See, we are going to take 6 real numbers, A1, A2, A3 and B1, B2, B3. See, I will take A1, A2, A3 as A, B, C, which are given real numbers. I am taking B1, B2, B3 as 1, 1, 1. So now we have 6 real numbers. So let us apply Cauchy's quartz inequality for these 6 real numbers. So by Cauchy's quartz inequality, you remember now that inequality says A1, B1 plus A2, B2 plus A3, B3 whole square less than or equal to A1 square plus A2 square plus A3 square into B1 square plus B2 square plus B3 square. So what will I do now? I will put their values. A1 is A, B1 is 1, A into 1, A plus A2 is B, B2 is 1, B into 1, B plus A3 is C, B3 is 1, C into 1, C square less than or equal to. What will happen here? We have to put values of A1, A2, A3. So we have those values. So A square plus B square plus C square. What about this bracket? B1 square plus B2 square plus B3 square. See, all of them are 1. So we will have simply 1 plus 1 plus 1. We have a space. Let us use it. So therefore, a plus b plus c square less than or equal to, getting 1 plus 1 plus 1, 3 we will have, 3 a square plus b square plus c square. Yes, we have proved the same thing, but they have just simply they have written in this way. So 3a square, same thing we can write in this way, b square plus c square greater than or equal to a plus b plus c whole square. So in this way we have completed this example. Make a screenshot of it. After that we will stop. Thank you. Bye bye.